Welcome everybody to my seminar. So here I'm going to introduce our recent works on the morphological intelligence in locomotion, from information theory to mesoscale robots. So here's a mesoscale in the title. So before I go on and on about the design and control in the mesoscale, let's first define what is mesoscale. And it would be better if we can start by appreciating the remarkable biodiversities. Animals with diverse sizes and shapes all moving well in their habitat, all the way from the worms to the centipede, the reptiles to the quadruped. However, this remarkable biodiversity is not yet reflected in their robotics counterpart. Here are some recent literature reviews on the robot body mass and the speed. As you notice, there appears to be two distinct clusters of robots. On the one hand, we can have the micro-robot, which typically has a weight less than 1 gram. On the other hand, we can have the macro-robot, which is typically more than 10 kilo. So, what about somewhere in between? We've noticed that there is a substantial research gap for a robot approximately 1 kilo, which we will refer to as the mesoscale robot. So with that, we have established that there is a research gap for the mesoscale robot. But who cares about the mesoscale robot? So to answer those questions, let me give you one example. We want to send the robot into those confined spaces in those collapsed buildings. However, the holes or tunnels are too tight for large robots. And in the meantime, to deploy the robot into those collapsed buildings, the robots still need to overcome those obstacles, which are too large for smaller ones. In this way, the capability to navigate confined spaces while maintaining high mobility makes the mesoscale robots well suited for diverse applications such as CBRN threat detection, which stands for chemical, biological, nuclear, and radioactive threat detection, which is projected to have 21.5 billion by 2028. The other major application for mesoscale robots is the precision agriculture. We want to send the robot into the farmland for precision operations such as weed removal, such as disease detections. And here's a concept map of a robot doing the weed removal. And in the meantime, we don't want to send big machines, which can simply destroy all those crops. So the precision agriculture can also have a huge market, which is projected to have 21.9 billion by 2031, with a particular focus on hardware. So there are more examples. Here's a fun one. Instead of grabbing for beers, how cool would it be if you can just ask a beer to come to us? We have the smart furniture. Here's a demo by Carpentier. But I have to clarify that this is not my apartment. This is my apartment. This plus the fact that we don't want a big cloaking machines in our living space. We want a mesoscale solution to our indoor clutters. And this list can go on and on, such as the mining safety inspection, such as the forestry management. So in other words, if we want to find a balance between the size and the performances, we should consider the mesoscale robot. So with that, we have established who cares about the mesoscale robot. We have established there is a real need for the mesoscale robot. But what has been stopping us? Well, it all comes down to the size. Here is the same corner of our campus taken from different perspectives. So let's for fun define a number. The number of active objects that we are continuously dealing with during locomotion. So now imagine if we are big, we are simultaneously dealing with more than 100 objects, a number large enough that allow us to consider them as a continuous medium, which substantially simplify their dynamics. And now imagine if we are small. Well, despite all the challenges in the micro-robot, it's only likely to deal with one object at a time. And now imagine, what about the mesoscale? Well, at this scale, the robot needs to interact with approximately 10 objects at a time. And each object has similar weight compared with the robot itself. This flow with the robot, which makes the terrain reaction forces almost impossible to predict, which will give us a noise-dominated regime. And the lack of tools to quantify terrain dynamics and uncertainty has been limiting us to develop effective mesoscale robots. So, how can we generate reliable locomotion in the noise-dominated regime? So that will bring us to the overview of my talk today. We believe the answer is the mesoscale embodied intelligence. In the first part of my talk, I will define what is the mesoscale embodied intelligence, which would include the bulky part of my PhD and postdoc work with Dan Goldman in Georgia Tech. In the later half, I will discuss our recent works on how do we generate embodied intelligence on demand, which include our recent work at Penn State. So, without further ado, let's get started with a mathematical theory of locomotion. So, speaking of a mathematical theory of locomotion, it would be wrong if we don't start with Aristotle, who stated that all moving objects will eventually come to rest unless an external power continues to move them, which of course was proven wrong. In Newton's law, the importance of inertia is highlighted. And it is the inertia that gave us the trains on tracks, the cars on roads, the modern matter transportation framework. There are two important features for the inertia-driven locomotion. The first one is that theoretically it can have infinite displacement per unit thrust. If here's a car, we give it a kick. Theoretically, in frictionless environment, it can go infinite displacement. In a frictionless environment, right? However, whenever there is friction, whenever there is the noise-dominated environment, it's less likely to expect good performances from the inertia-driven locomotion. So, what should we do? Well, as human, we take steps. By taking the steps, we effectively discretize the locomotion. In other words, there is an upper bar about the displacement that you can obtain per step. It's not infinite anymore. However, by taking the steps, we got to choose where to land our next feet. It offers a mechanism to counter the terrain heterogeneity. However, it is almost taken for granted that the computational intelligence, the capability to perceive and respond to terrain heterogeneity, is a necessary condition to facilitate the step-driven locomotion. And we wonder if that is universally true. Let me repeat. We wonder if the computational intelligence is a necessary condition to facilitate step-driven locomotion. And this is a very challenging question. To get more insight, let's take a step back and learn from signal transmission in information theory. How do we transmit signal over noisy channel? Well, it's also transportation with noise. So, there are many ways to transmit signals over noisy channel. First one is the continuous analog signal, which in principle can convey infinite amount of information per length of signal. We have the first derivative, second derivative, etc., etc., etc. However, the information carried by those continuous analog signal can be easily contaminated by the channel noise, such that our recovered signal can contain some error. As you already noticed, it is very similar to our inertia-driven locomotion. So smart people also propose to digitize the signal transmission into bits. And in doing that, there is an upper bar about the information that you can carry per bit. It's not infinite anymore. As you already see, it's very similar to our step-driven locomotion. So how do we facilitate reliable digital signal transmission? Well, there are two ways. First, here is a retransmission channel. A source transmits a signal, gets contaminated, and the source detects if the transmitted signal can contain some noise. If there is, it simply requests a new message to be retransmitted through the retransmission channel. A feedback system, very similar to our computational intelligence. And Shannon argued that we don't need any feedback at all. Instead, the redundancy in the coding is sufficient to drive reliable digital signal transmission over noisy channel with error rate arbitrarily close to 0. So we've learned a principle that it is possible to expect reliable transportation without feedbacks. And now we wish to generalize this principle to locomotion. In other words, if a locomotor is sufficiently redundant in the morphology, like those many legs, is it possible for it to go over complex terrains without any feedbacks at all? So here we would like to introduce a mechanism which we define as the morphological intelligence, which is the passive response to environmental perturbations governed by the physical laws or the morphological constraints. Let's see how those morphological intelligence will bring us. To quantify this, we establish an analogy between signal transmission and locomotion. We start with a very brief overview of signal transmission. To transmit a message, we first need to encode the message from ABCD to some binary bit sequence. And then we transmit this binary sequence over noisy channel, gets contaminated. And now we wish to estimate the original message over those contaminated received bits through the decoder. And Shannon told us that with sufficient redundancy and appropriate coding, the estimated message W dash can be arbitrarily close to W, our original message. And here, to make the analogy between signal transmission and locomotion, the key insight is to take an analogy between a bit to a step and model a step as the discretized thrust input. So let's see how it goes. We have a locomotion task. The robot needs to go from point A to point B over some distance. That's our destination, our desired destination D. To go there, we design some spatial temporal distribution of the steps, which tell us when and where should we land a step. And here, the morphological redundancy is effectively how many steps do we have at each instantaneous time that's repeating itself. So as the robot implements those stepping maps, it gets contaminated such that the actual stepping maps can be deviated from the original ones. And that will lead us to the actual destination D dash, deviated from our original destination D. So our goal is to demonstrate that the D dash, the actual destination, can be arbitrarily close to D, our desired destination. So, follow the similar derivations as Shannon did, we've reached our conclusion that reliable and predictable locomotion can be probably generated over noisy landscapes without any feedbacks at all if we have sufficiently many legs. And philosophically, it's in line with our story, the thrust-dominated matter transport. And we have a lot of theory. Here, talk is cheap. Show me the robots. Here, I will show you some of our robot experiments. So we have all these robots from 6 legs to 16 legs. And we record the time required for this robot to travel 60 centimeters. The arrival time is plotted on the y-axis. And we notice that on flat ground, there's not much of a difference from 6 legs to 16 legs. However, if we challenge those robots on complex terrains, the advantage will emerge. Like we see on the top panel, if the robot we are lucky, for the 8-leg robot, it will be just fine. However, if we're not lucky, the robot will get stuck very easily. However, if we look at the bottom panel, the 16-leg robot will have the consistent velocity output. It is also supported by the distribution of arrival time. The lower bar doesn't change much. It's that if we are lucky, we can just arrive on time. But the upper bar decreases substantially as we increase the number of legs. And the math told us that the upper bar and lower bar will converge to a single point. And that converged point is our guaranteed locomotion. Which means that if we want a robot to go from point A to point B in 10 minutes over complex terrains, the robot will go from point A to point B over complex terrains in 10 minutes sharp. And in this way, even the wind-powered sculptures, the strand beast, can be as reliable as we want it to be. How cool is that? And that's the morphologically intelligent robot. And before we put our morphologically intelligent multi-leg robot into practice, we've noticed there's a major drawback, which is this robot are too slow compared with the conventional quadrupedal robots. To make our robot into practice, we need to find a way to make the robot faster. So in other words, we have established that if we have more legs, which is a morphological feature, so that will give us more robust locomotion over complex terrains, which is quite intuitive. Now, we wonder if for the same morphological feature, which is having more legs, can that feature will give us higher speed, which is not intuitive. Because intuitively, in order to achieve higher speed, we want longer legs instead of more legs. In other words, in order to achieve higher speed, we want another morphological feature, which is longer legs, instead of this morphological feature, which is more legs. So to put into more context, we wonder, is the morphological intelligence defined over a specific task? In other words, what is the relationship between the morphology and the performance? And this is a broadly interesting question, and not only for the roboticist, but also for the biologist. So let's see what the biologists have concluded for this question. So let's take a look at the origin of the biodiversity. So there has been a well-established hypothesis stating that each morphology is particularly suited for a specific environment. So this means that the diversity of animals we see today reflects the diversity of the environmental niches that the animals will encounter every day. So if this hypothesis is true, then it's likely that the morphological intelligence, yes, it's only defined over a specific task. So let's see how this hypothesis has been challenged over the years. Of course, this hypothesis has a long history dating all the way back to Darwin and also the Arnold in 1963. And in the recent decades, the biological community has challenged this hypothesis, which effectively assumed a one-to-one mapping between the morphology and the performance. So the challenge can be, the list of challenges can be long, And let me demonstrate this by showing you this video. The lizards and snakes has dramatically different morphology. Yet, in the same environment, they achieve very similar performances over different tasks: jumping, walking, running, climbing. So this indicates that the mapping between the morphology and performance can actually be a many-to-many mapping. In other words, for the same morphology, animals can use different strategies to achieve different performances. So let's see how this perspective can challenge our argument, the hypothesis about the origin of biodiversity. So alternative hypothesis is that animals with various morphology can achieve broadly equivalent performances across different environments. So in this way, the biodiversity may instead reflect the historical contingency. This good enough equivalent performances across different environments may in fact preventing the animals to evolve to a single optimal morphology. So I realize this is not biology similar. So let's discuss how this alternative hypothesis can inform us with the robot morphological intelligence. So if the alternative hypothesis is true, then we can argue that it's not likely that the morphological intelligence is only defined for a specific task. In other words, depending on the way we control the multi-leg robot, we could achieve higher speed. But how exactly are we going to do that? And here we can take inspiration from biology. Here, as expected, centipede can achieve good performances, reliable performances on the complex terrains. However, if we put the centipede on the flat ground, it changes the way it moves. And in fact, the speed on the flat ground is actually 3 times faster compared with their performances on the flat ground. How do they do that? Well, here, let's imagine that there are no legs. And if we just focus on the body and we look at it, it looks like a swimming, except it's swimming in the terrestrial environment. And we would like to use some tools from fluid mechanics to understand how centipedes coordinate their body and leg movement to generate terrestrial swimming. So, in the fluid mechanics, the swimming has 2 regimes. The first one is the inertia-driven swimming, like those in the eels. This movement is dominated by the momentum. The other one is the viscous-driven locomotion, like what we see in the nematode worms. It has to continuously generate locomotion, generate the thrust against the environment drags. So can we make a guess? Would the centipede terrestrial swimming closer to the eels or closer to the worms? Anybody? What is it? Viscous. Yes. Well, it's more closer to the viscous. And how do we quantify that? So let's first quantify the role of inertia of centipede terrestrial swimming, and then come up with a way to reconstruct the centipede terrestrial swimming on robot. So to quantify the role of inertia, let's define a number. We define the coasting time, which is the time required for the locomotor to reach a complete stop after they stop wiggling. Okay? The coasting time. If we normalize this coasting time with the characteristic timescales, such as the average cycle time, we can obtain a dimensionless number, which is our coasting time. And we derive that in the viscous environment, our coasting number is directly related to the Reynolds number, a well-established dimensionless number in the fluid mechanics to quantify the role of inertia. Of course, one good thing about this coasting number is that it can be easily generalized to the terrestrial locomotion, and we can estimate the coasting number for the centipedes. And here our estimation, and we've noticed that our centipede has the constant number substantially less than 1, which allows us to safely ignore inertia. So we can argue that their locomotion is dominated by the consistent generation of thrust against the environment drags. And then the more important question is that how do centipedes coordinate their body and leg movement to generate the thrust? Well, again, this is a very challenging question. To give more insight, let's take a step back and learn from what the Purcell would say for life at no Reynolds number.
Yes. Yeah.
So you have a coasting number. You talk about whether the locomotion is more inertia-driven or viscous-driven.
Correct.
But in fact, it's not viscous, it's friction.
It's friction, yes.
Which is independent of speed.
Yes.
So, that being the case, does that make things any different?
So we're trying to, we're trying to argue that it's a thrust generation is more important compared with the inertia forces. We're comparing the thrust. So, okay. So now, in the regime of no Reynolds number, which the thrust generation is dominating over the inertia, so Purcell argued that the net locomotion is uniquely determined by the sequence of shape changes or the posture changes and does not depend on how fast or how slow the sequence is implemented. This allows us to allow us to look at the sequence of shape changes of the centipedes. By carefully examining the shape changes for the centipede, this can allow us to reconstruct the terrestrial swimming on the robot. And this body-driven locomotion on the centipede robot is actually 3 times faster compared with the leg-driven locomotion as we've seen before. So with that, we have established that having more legs, depending on our controls, can give us either higher speed or more robust. Now we became more greedy. We wonder if having more legs can give us not only higher speed, but also more robustness. So, according to the theorem of no free lunch in optimization, it might be too much to ask to optimize for the 2 objectives if we are only allowed to modulate the morphological intelligence. So how about we equip those already morphologically intelligent robots with some computational intelligence? And for that to happen, we need to answer 2 most important questions. That is, what to sense and how to respond. So, let's start by looking at those terrestrial swimming. It has good performances on the flat ground, but they struggle a lot on complex terrains. In the same time, if we change the way we control it, we can have reliable performances on the complex terrains. However, it's very slow on the flat ground. So how about we adapt the way we control the centipede robot depending on the estimated terrain complexity and have some computational intelligence? So to do that, we have some contact sensors at the feet of the centipede, which can tell us whether a contact is being made or not. Because we have so many legs, we can collect the stepping maps telling us the spatial temporal distribution of the steps. And if we compare the actual stepping maps to the desired stepping maps, this difference will allow us to estimate terrain complexity. And then we can build a very simple linear feedback controller. If we implement this linear feedback controller, we notice that it substantially improves the locomotion performances over the complex terrains. And in later work, we demonstrate that this linear feedback controller can be recasted as the majority voting code with adaptive window size in signal transmission. In other words, we've demonstrated that this linear feedback controller not only improves the performances, but also preserve the feature of guarantee. And in more recent work, we've noticed something very interesting. that a 16-leg robot with no feedback controls at all in the same environment will have the similar level of performances compared with a 12-leg robot with a feedback controller operating at 0.1 Hz, with similar level of performances compared with an 8-leg robot with a controller operating at 0.5 Hz. This suggests that there might exist some functional equivalence between the morphological intelligence and the computational intelligence. So with that, we've noticed that there is an emergent embodied intelligence with different distributions of morphological and computational intelligence. But that's not the end of story. We've become more greedy. We want to generate the embodied intelligence on demand. In other words, if we were given some constraints on the speed and the robustness, can we co-design the morphological and computational intelligence towards a better performances? And for this to happen, we need to answer two questions. First, how do we control the unconventionally shaped robots? And second, can we quantify the benefit of unconventional shape robot morphology? And this is, of course, an open question, and I would like to share my perspective through 3 examples. The first one is how do we adapt sensing modality to morphology? And second is how do we go beyond taking inspiration from biology? And finally, how do we use physics to generate new principles beyond taking the principles from biology? So let's get started with adapting sensing modality to morphology. Inspired by those very cute creatures, our reptiles, we have designed our Skink robot. Our Skink robot has a feature of tiny legs attached to the elongate body. With this morphology, we hope this robot to merge the benefit of a snake robot and a quadruped robot. Of course, the question becomes, how do we control this unconventionally shaped Skink robot? We've designed some different ways to control this robot, all the way a continuum from the standing wave on the top panel to the traveling wave on the bottom panel. We test them on a flat ground. So on the flat ground, we noticed that it would be more beneficial to have a standing wave compared with a traveling wave. This denotes how the wave propagates down the body. It's also supported by our data. You see that if we go from standing wave to traveling wave, from right to left, we have less speed. So this is our conclusion on the flat ground. Of course, the whole thing, the whole benefit of having a Skink robot is for it to locomote on more challenging terrains, such as those deep granular media. So for the same control, we test all those from standing wave to traveling wave and have this robot locomote on the deep granular media. And we notice that the advantage of having traveling wave will emerge. It is also supported by our data. You see that on the deep granular media, we should use a traveling wave. So that's the conclusion for the deep granular media. So how about somewhere between the deep granular media and flat ground, which is a shallow granular media? Seems like in the shallow granular media, we should use somewhere between a standing wave and a traveling wave. So with that, we have established our first conclusion, that Skink robot should transition from standing wave to traveling wave as it moves on the deeper granular media. Our next question is, how should Skink robot estimate the depth of granular media? So my graduate student came up with an idea. So he measured the torque distribution on the body. And our theory suggests that on the deep granular media, the torques should be concentrated on the middle part of the body. And on the flat ground, the torques should be evenly distributed all over the body. So with those insights, we can design a very simple classification method, the KNN, with the accuracy up to 90%. So in this way, we have reached our second conclusion, which is for the Skink robot, the torque distribution on the body can accurately predict the granular media depth. So we know what to sense, and we know how to respond. So very natural that we can build a feedback control. And here is a demo of how our Skink robot can adapt the way it moves from flat ground with a standing wave to the traveling wave on the deep granular media based on the estimated terrain granular media depth based on the torque distribution on the body. And here we notice that for the Skink robot with very tiny legs, the torque distribution on the body can accurately predict the granular media depth. If we compare our conclusion to a conventional quadrupedal robots, which have long legs, their conclusion is that the torque distribution on the legs can accurately predict the granular media depth. So this tells us that as we decrease the limb size, the sensing modality should transition from the legs to the body. In the concurrent work, we're trying to study and quantify when and why and how should the sensing modality change as we modulate the morphology of our Skink robot. So with that, that's the end of my first story. And this is all very bio-inspired. So let's see what should we do if we can go beyond taking inspiration from biology. So previously, we have established that having more legs can give us higher speed. But can we actually quantify the benefit of having more legs? Well, here we experimentally quantify the top speed that we can obtain by varying the different amplitudes, the top speed of multi-leg robots, and plot that as a function as the number of legs. And from there, we notice that if we increase from 3 pairs of legs, the hexpot, to the 4 pairs of legs, we can still have some good amount of improvement. However, the marginal benefit to increase more legs will decrease as we increase the number of legs. And it will eventually saturate. In our specific case, it saturates under 7 pairs of legs. So this is not good. We wonder if there's something fundamental laws that limit the speed limit of a multi-leg robot, or we are constrained by our own intuition. To get more insight, let's take a step back and learn how we have arrived here. As we introduce more legs to the multi-leg robots, we substantially increase the dimensionality. And that's a good thing and a bad thing. It's good because we have a larger space to explore. And it is bad because we lose our intuition. And it is with reference to the biology that we can boldly explore those higher dimensional spaces of multi-leg robots. And one thing I've learned in the recent years is that taking inspiration from biology is not about just mimicking the biology. It's to answer the question of when should we transcend biology. That is, despite the complexities, animals need to follow some rules of life, which robot doesn't have to follow. We should think out of the box and ask what should happen if we can break some rules of life. For example, yes, there is a fundamental limit for the forward movement if we have some assumptions on the symmetries. However, we don't have to go forward. If we go sideways, the speed will grow linearly as a function of number of legs. And more importantly, here, having longer legs will not give us higher speed. Instead, if in the extreme case, a limbless robot can curl into a helix and they can develop this angular momentum and roll like a wheel, can generate those very efficient and fast locomotion method. So with that, we have established that, well, there are some benefits to transcend beyond taking inspiration from biology. But without reference to biology, how can we systematically explore the whole dimensionalities associated with multi-leg robots? So that will bring us to the last part of my talk today. How do we use physics? Well, let's start with the hexapod. Because of the curse of dimensionality, whenever we think about a hexapod, we typically think about the coupled cases. Those 3 legs are almost coupled, and those 3 legs are coupled. It's very rare to see a hexapod robot with independently controlled legs. So here, we are going to use physics to explore what would happen if we can independently control every leg. And this is a very challenging question, because we are dealing with a huge number. Let me explain what a large number that we are dealing with. So the n is number of legs. The total number of contact states is 2 to the power of n. It's not very scary yet. However, if we take a look at the total number of contact state combinations, and that is a huge number. For hexapod, this number is 2 times 10 to the power of 89. And this large number has been substantially ignored because who cares? Most of those contact sequences are not going to be useful. But how can we know a priori that those sequences are not useful? Well, we can take inspiration from biology. Of course, here we're going to explore what would happen if we can explore the full contact state sequence space. And for that to happen, we need to understand why contact change can give us locomotion. The recent advance in the physics and in the geometry of locomotion has given us this conclusion that in the isotropic environment, such as the Coulomb friction, if there's no contact change, there's no net locomotion. As you see here, the robot can turn in place, but they cannot generate effective locomotion without contact change. So this conclusion can substantially simplify the locomotion. So we can define a graph. We can define the vertices as the contact patterns. We can define the edges as the net displacement resulting from the contact switch, and which the value of the edges can be numerically and experimentally evaluated, and we can convert the locomotion problem into a well-defined graph optimization problem. And before I present you our graph optimization results, let's first understand what would happen if we constrain ourselves with bio-inspiration. The biology is all about symmetry. For example, we have contralateral symmetry, which is my left leg and the right legs on the same side. They are coupled. They are symmetrical. If we turn clockwise for one half of a cycle, we turn counterclockwise for another half of a cycle, such that the robots will go straight. And we wonder if that's a necessary condition for us to control a hexapod robot. Well, our graph optimizer is not aware of those contralateral symmetry. In fact, our optimization tells us that it is asymmetry that will bring us the fast locomotion. The robot will turn clockwise for 3/4 of a cycle and rapidly counterclockwise for 1/4 of a cycle. And more importantly, if I take a look at those 2 legs pointed by an arrow, we notice that those 2 motors are fixed. They never move, never change, never over the course of the locomotion. Which means that we can simply replace those 2 motors with non-actuated rigid parts. So in this way, we can design this very weird quadruped with 3 legs on the one side and one leg on the other side. This can achieve 50% faster compared with the conventional symmetric locomotion, and it's very asymmetrical. And in fact, it's the asymmetry in the morphological intelligence plus the asymmetry in the computational intelligence that can give us the reliable locomotion. And we believe our method can be generalized to any cases where the slippage is inevitable, like those in the snow, which we see very often in Pennsylvania. See that those robots can generate effective locomotion over the snows based on those asymmetry in both morphological intelligence and the computational intelligence. So with that, I would like to wrap up and provide a very brief summary to what we've discussed today. We first discussed what is a mesoscale robot. It's a robot approximately 1 kilo. And who cares about the mesoscale robots? The mesoscale robot provides a balance between the performance and the size and the potential to navigate the confined spaces with the high mobility. And what makes the mesoscale robot so challenging? Well, it operates in a noise-dominated regime. How do we generate reliable locomotion in a noise-dominated regime? The first method is the computational intelligence. And we show that we have an alternative solution is to have the morphological intelligence, which is another way to deal with the terrain heterogeneity. And towards the end of my talk, we've discussed our recent works to how do we generate the embodied intelligence on demand with some different distributions of the morphological and computational intelligence towards the future highly effective mesoscale robot. So with that, I'd like to wrap up and provide this great thanks to my great students and also the Professor Dan Goldman for training me well. Thanks.
Yes.
Thank you very much for the talk. I was wondering if you looked into how changing the length of the actuated legs or the ratio between the distance between pairs of legs and the length of leg would also really affect the morphological intelligence that you mentioned on your non-actuated legs. That when you don't have legs, the robot can curl and actually move faster. Or is that still like how did you design the mechanical aspects of your robots usually?
That's an excellent question. So we're changing, for example, the leg spacing and leg length. So that's some way to modulate, for example, the leg size. So that's, of course, another feature that we can play around with the morphological intelligence. And so in the first part of my talk, I just fix that and just to explore what would happen if we have redundancy. So we're trying to say that no matter how good or bad you are as an individual module, if we have sufficient redundancy, yeah, all good to go. Yep. Yep. Yep.
When thinking about the different kinds of locomotion, I was thinking about how crocodiles, if they want to go really fast, they can gallop or even bound. It's amazing. It's like between 4 and 5 meters per second.
Yeah.
But they're using a really different locomotion. They have an airborne phase. So now there are insects that jump, but not millipedes or centipedes that I'm aware of. And what about, and so that's interesting. Is there something about that morphology that makes it energetically prohibitive to have an airborne phase? Or, I don't know, I mean, even with your little robots, if the servos were much more powerful, could you not do jumping? And then, of course, we'd go way faster.
That's an excellent question. So we're gradually exploring the cases if we have want to have more dynamic phases. So, for example, so even for the conventional quadruped robot, if we have it on the moon, it will just hop up and down, right? So that's we believe that's not efficient way for locomotion. We believe an efficient way for locomotion, if we just care about the cost of transport, it should just move like lizards. Because lizards can hop very high, but when they choose to go fast, they use some combinations of their tail movement to justify, to reduce the center of mass oscillation for fast movement. So we're trying to identify the different modes of locomotion, different regimes of locomotion as a function of morphology, and of course, how do we modulate different regimes, even within the same morphology.
Kind of a terminology question, and this is coming about because I was just at Berkeley on Wednesday talking to Bob Fold, who is very concerned about the the terminology that we use to describe embodied intelligence and such. So, do I understand correctly, your equation said embodied intelligence equals more
Morphological.
mechano or
Morphological.
intelligence plus computational intelligence. And I do feel like embodied intelligence is sort of come up to maybe to mean something different now, right? Like a humanoid with AI in it. And I was just curious, do you have any other thoughts about what is the right way to describe this kind of physical intelligence?
Yes, so that's of course excellent question. First, Bob, we had this discussion with Bob as well.
Okay.
So the way that we choose, like to say that is embodied intelligence can be described as a sum of mechanical or morphological intelligence plus the computational intelligence, is that it can be a quantifiable way for us to quantify the intelligence. For example, we can have the mechanical cost of transport. We can have the computational cost of transport, such as the computational need you will have for a robot to go from point A to point B. If we can compare the cost of transport as a sum of mechanical and computational cost, then we can have the quantifiable way to distinguish different intelligences. So that would be my rationale of choosing the morphological intelligence or mechanical intelligence and embodied intelligence and the computational intelligence. Yeah. Thanks.